In this module, we will see why concurrency is hard and how sharing of memory between the threads can create lot of complexity. If you remember from the previous module, you know that all the threads share the same address space. They share the heap and the data region of the process. And threads communicate between each other by sharing memory. But this sharing of memory creates a lot of complexity with concurrently executing threads. So if two threads are running concurrently and they try to access same area of memory with one thread trying to write to the memory, then there will be a data race and the outcome of the program will be undeterministic. Let us consider an example where thread 1 and thread 2 are running concurrently, and here they are trying to increment the value of a global variable I. The increment operation is not atomic. At the code level, it looks as a one statement, but in the context of the machine instructions, it involves retrieving the value of I from memory, incrementing the value of I, and storing the value of I to the memory. So what happens if the thread gets preempted between these operations? So let us see some scenarios. Now let us take two sequences of execution. In the first sequence, thread 1 and thread 2 are executing sequentially, one after other. In second sequence, thread 1 and thread 2 are executed in interleaved fashion, where execution of one thread is preempted by the other thread. Let us consider the first scenario. Thread 1 starts the execution. It retrieves the value of I, which will be 0. It increments it and then stores the value of I. Then thread 2 comes along. It retrieves the value of I, which will be 1, and it increments it by 1, and it stores the value of I, which will be 2. This is fine. Now let us consider the second scenario. Thread 1 starts the execution. It retrieves the value of I, which will be 0. Then it increments the value of I to 1. But before thread 1 can write the value of I to memory, it gets preempted. And thread 2 starts the execution. It retrieves the value of I, which will be 0. Then it increments it and it stores the value of I as 1. Now thread 1 comes along and it will store the value of I as 1. As you see, the value of I can be 2 or it can be 1, depending on how the threads are executing. So concurrent access to memory leads to undeterministic outcomes. So one way to handle this will be to use memory access synchronization tools. We need to guard the access to the shared memory so that a thread has an exclusive access at a time. And we need to force thread 1 and thread 2 to run sequentially to increment the value of I. We can do this by putting a lock around the increment operation. Putting a lock around the shared memory is a developer's convention. So anytime a developer wants to access the shared memory, they need to acquire the lock. And when they are done, they need to release the lock. If the developer does not follow this convention, then we have no guarantee of exclusive access. And it can always happen that some code can always sneak in which does not follow this convention, and we hitting race condition at some time. There are other problems, like locking actually reduces the parallelism, as locks force the threads to be executed sequentially. So the critical section where we access the shared memory becomes a bottleneck between the threads. The other problem is coding mistakes. Inappropriate use of logs can lead to deadlocks. Let us see an example. Here, there are two threads executing concurrently. Thread 1 starts the execution. It takes a lock on resource v1. It gets preempted by thread 2. It takes a lock on resource v2. Now thread 1 comes along. It wants a lock on resource v2, but it is not available. So it goes into the waiting state. Now thread 2 comes along and it wants a lock on resource v1, but it is not available. So it also goes into waiting state. So as you see, this is a circular wait which leads to deadlock and the application will just hang. So we have come to the end of this module. Let us summarize. So we saw why concurrency is hard. Sharing of memory between the threads creates complexity, and concurrent access to the shared memory can lead to race conditions and outcome can be undeterministic. Memory access synchronization tools actually reduces the parallelism and comes with its own limitations. We are done for this module. See you in the next module.